representation as Daniel said. Okay. Sí,
y esto, pues para aquí ya está.
sí, ya está. Vale, ya está. ¿Sí? ¿Se oye? Do you want me to continue for when or? Okay. So start from here. Okay. So, well, as I was saying, complex networks have been widely used, and they represent in a really schematic way. With nodes, we represent entities or individuals, and it represents the interactions, which are represented by links. So the point is that in ecological systems, it's quite common to have abrupt transitions or hysteresis cycles and similar kind of transitions. And these transitions are not that common in the normal complex networks. And this is the main reason to go to what are called higher order interactions. And among these higher order interactions, we find the hypergraphs. And in hypergraphs, it has been shown that those kind of transitions are more common. So when we talk to hypergraphs, or when we talk to higher order transitions, we mean that many nodes interact at the same time. While in complex network, we have the limitation that the interactions were among pair of nodes. So just by assuming this, we can assume two different situations. The case in which the interaction is simultaneous, so all the nodes are acting at the same exact moment, or we can assume a slightly different point of view, which is the time scale difference, and in fact is the one that we are going to consider in this thesis. And with time scale difference, we mean that if the frequency of the interaction is much faster than the characteristic time scale of the system, then we can consider that those interactions are happening in an instant, and we can assume this interaction of all the nodes at the same time. So, of course, I'm talking about advantages with higher order interactions and the better fidelity when reproducing the systems, but it also has some disadvantages. And mainly they are that the mathematics in the field are not that well developed, and the computational packets neither are. In fact, most of the algorithms, almost any of the algorithms used in this thesis have been programmed specifically with the purpose of developing the thesis. So, well, I have mentioned higher order interactions. I have talked about hypergraphs. Did we have any other option? Well, we have the simplicial complexes. But the point with simplicial complexes is that they assume that inside an hyperedge, all the nodes contained in that hyperedge need to have pairwise interaction among them, some pairwise links. And this was proven false in the data we will work with. And this is the reason to keep with hypergraphs. And I have mentioned them, but this is the mathematical definition. It is composed by a set of nodes, and it is composed by a set of hyperedges. And the set of hyperedges, it is composed by subsets of nodes. So just to assume a simple hypergraph, we want to keep that the hyperedge needs to have no direction, which means that if we have an hyperedge between I, j, and k, that interaction is among all the nodes, not from I to j and from j to k, for instance. And if we need to have no repetition, and the size needs to be larger than 1. So we do not have what in complex pairwise network is called reflexibility. I also mentioned in here bipartite graphs. And why do I do so? Well, because in fact, bipartite graphs are really connected to hypergraphs. And this is because bipartite graphs, which is a specific kind of complex network, are divided, the set of nodes is divided in two subsets. And one subset interacts with the other one, but they do not interact among the same subset. So in here, you have an example. And the point with these bipartite graphs is that you can project them into an hypergraph. To do so, we can assume that one of the subsets will be the nodes in the hypergraph. And for instance, in here, we have V1, V2, V3, which are going to be the nodes of the hypergraph. And then we have E1, E2, and E3, which will act as the hyperedge in the hypergraph. Then in the last picture, we just have what is called the star expansion, which is just another way of representing the hypergraph, and is the way in which we are going to perform our representations, because it is clearer when it comes to plot big hypergraphs. So of course, we also need to understand some basic ecological concepts in order to understand the results. And well, I'm sure you all have heard about ecosystems, but it's not exactly the system we're analyzing, because an ecosystem includes all the species and includes the environmental factors. We are not considering the environmental factors, but just the species and the interactions among them. So these are what are called the communities. And those interactions that I'm mentioning can be divided in two big groups that are the competitive interactions and the mutualist interactions. Basically, in a competitive interaction, one individual wins and the other one loses. And in the mutualist interactions, both individual wins, or at least one of them wins and the other one do not lose anything. So these big groups can be divided into subgroups. And I have chosen in here 6 because those 6 interactions are the ones that we are going to have in our networks. So the pollination, the dispersal, and the symbiosis are mutualist interactions. The two first ones are mutualist interactions that participate in the stages in the reproduction of the plant. In the pollination, we move the pollen, and in the dispersal, we move the seed ready to germinate. Well, in the symbiosis is an obligate mutualist interaction, which means that it needs to be here for the, in this case, are going to be plants and fungus, for the fungus or the plant or both to survive. In fact, the symbiosis also has the characteristic that it needs physical closeness. Then we have the predation, the herbivorous interactions, and the saprophytic interactions. And those are competitive interactions. The predation and the herbivorous are closely related. The predation is considered to be more general. In here we call predation to an animal consuming another animal. So it is a relation in which we have a predator and a prey. The predator devours the prey. And the herbivorous specifically is from an animal and a plant. And then we have the saprophytic interactions. The saprophytic interactions are parasitic interactions in which we also require physical closeness. And in here, in this thesis, is also going to be of fungus attaching to a given plant. And in these interactions, the fungus eats the dead tissue of the plant, which could seem something positive, but it's not, because in general, these interactions causes diseases on the host. So in this case, on the plants. We also want to clarify the concepts of generalist and specialist. And generalist is an animal or fungus which can consume many different resources, while an specialist is an animal or fungus which just can consume a few of them. So now that we understand the interactions, we can jump into the proper data. And the data is provided by the Travesell lab in the media, and it's data from here, from Mallorca. It's consistent on 6 bipartite networks of interactions. Then interactions that we have defined before, and the bipartite that we will project into hypergraphs. In here, you have the original data. And among all these networks, the only one that is not plants with an animal or fungus is the predation, even though I have put it in here. And the point is that when we perform the projection on the plants, that in this case are not plants, remember, we obtain a null hypergraph. So in general, the predation network have a lower statistic and will not be considered in many of the measurements that we will talk about. The other ones can be projected on the plants, as I have said. And if we project all of them on the plants, then we have what is called a multi-layer, in which each layer is an hypergraph with a specific kind of interaction. And they can share some of the nodes, which in this case are plants. So what we can do is combine all these layers to create what is called the aggregated graph, in which we will also perform some of the measurements. So now we jump into the proper results, and first we have to do is to perform the representations of the networks. And in here, bottom left, you have the hypergraph for the aggregated graph on the plant projection. So all the nodes are plants, and the hyperedge are some kind of animals or fungus. You have 3 nodes that are repeated more. The color of the node represents the repetition in the different layers. So these 3 nodes repeat in the 5 different interactions. And this is important because if the node repeating more interactions, it can be considered a more important node because the extension of that plant, of that node, will imply an effect in the 5 different layers. We also have plotted the dispersal and pollination interactions because even both of them are stages on the reproduction. We observed that there didn't seem to be much nodes in common. So this implies that if a plant pollinates via animals, then it will try to disperse via any other method, such as wind dispersal or water dispersal or any other environmental method. We also have plotted these networks because they contain most of the nodes that are in just one layer. So the point is that, especially in the dispersal network, you observe that outer structure that is composed by nodes in just one layer. And the extension of those nodes is not expected to have much of an effect in the rest of the layers. But in here, take into account that we are just considering direct interactions. We do not take into account indirect interactions that are really common in ecology. So an species extends and it generates a cascade of extinctions. We cannot consider that with the measurements we are going to talk about. Well, I was talking about the importance of the node, and an easy way to measure the importance of the nodes is by measuring the degree and the hyperedge order. The degree is the amount of hyperedge that connects to a given node, and the hyperedge order is the amount of nodes that are contained in an hyperedge. Just by convention, the hyperedge order is that amount minus 1. And they are closely related because when we perform the projection, the degree in one layer corresponds to the hyperedge order in the opposite layer. So just by knowing one of the measurements in both layers, we can know the other one. They are complementary. So in here, I have written the hyperedge order on the plant projection, and the last 2 columns represent the hyperedge order in the aggregated graph. And I have ordered in such a way that the first node is the one that has the highest degree, so the largest amount of connections. And well, this is important. This is the way of measuring the importance of the node, because if that first node, in this case, the Withiana frutescens, gets extincted, it will have an effect on 316 different animals or fungus. So in this way, we can know the importance of the plants and the animals fungus. Since we already have the hyperedge order, we can also plot the hyperedge order distribution. And for the aggregated graph, it could be fit to an exponential function. And this is interesting because it means that there is not a natural cutoff. So remember, we are working on the plant projection, so the hyperedge represent the animals. And the largest the hyperedge means the more generalistic the animal is, because it consumes more resources. And seems to be that in larger ecosystems, we can expect animals and fungus which are even more generalistic. So there is no a cutoff in which the animal do not keep generalizing, let's say. We are also interested in knowing if this behavior is in the aggregated graph or also in each individual layer. And well, the individual layers have not enough statistic to perform a fit or a proper fit. So what I plot in here are heat maps in which we have in the y-axis the plant, and in the x-axis we have the hyperage order. And if a plant has a given hyperage order, we mark it. And the intensity of the color represents the amount of those hyperage orders that we have. And I have plotted these two because they seem to have a non-exponential behavior. In fact, look at the dispersal network, the one on the top. It has larger hyperedges with no lower hyperedge orders, which is, of course, a non-exponential behavior. And in the pollination network, it happens similar. In this case, we have the lower orders, we have a large order, but we have a huge gap in the middle. So even though we cannot fit them, we can observe that the exponentials, that the behaviors do not seem to be exponential. We are not just interested in how the plants interact with the animals, or how the animals interact with the plants, but also on how they interact among them, so animals with animals. And to know that, we can look at how the hyperedges are distributed. And a way to see how they are distributed is to look at the entropy. The entropy measures in a given node how many different hyperedge order converge into that node. And just because in the plots we take the exponential of that measurement that I present in here, we can be in y equals to x, which means that the nodes, the hyperedges are completely mixed, or we can be on y equals to 1, which means that they are not mixed at all. Of course, all the measurements in the middle are allowed. And what we observe is that in some of the network, there seemed to be a tendency to be more mixed. But to know that for sure, we need to compare with a null model, because most of these cases could be explained by the structural characteristic of the networks. But instead of comparing this measurement with a null model, what we do is going to an even more specific measurement, which is the overlap. And in the overlap, we measure the amount of nodes in common between two hyperedges. And just to normalize it, we divide by the maximum possible amount of nodes that they can have in common. So in here, you have an example of this graph. We have the different orders. The larger the point means the larger the statistics, so the higher amount of those hyperedge orders that we have. And the point of this measurement is that we can calculate the null model mathematically. So it's an hypergeometric distribution. And what we observed is that there were non-significant deviations, meaning that most of them were within one sigma deviation. But for instance, look at this, that is the order 6, with the order 6 that are those pink dots. We observed that they all seemed to be above the average. So what we did was counting the number of data above the average, below the average, and on the average. And is what I present in that table over there. And what we observe is that there seems a tendency, that we were talking about, to share nodes more than in a null model. And sharing nodes mean that they are sharing resources, which in some kind of interaction, it's a quite shocking result, because think on the symbiotic network, on the plant projection. A fungus wants the plant to be alive and in the better conditions possible. So that fungus do not mind that there is another fungus attached to that plant. It's good for both of the fungus and for the plant. But now think on the pollination. I have said that the pollination is a mutualist relation, and it is between the insect and the plant. But it is not between two insects that want to collect the same plant, because the plant, the pollen, is a limited resource. So what we would expect is that, in fact, the insects fight for the resource. So we will expect that that number was below the average, but we have more statistic above the average. So it means that even in a competitive interaction, same happens with saprophytic, they are sharing the resource. Just to look at this in more detail, we can look in the case of specialist animals or fungus. And we do that by looking at the motifs, the same motifs presented by Uri Allen in his biological transcription networks. We can expand them to hypergraphs, and we have these 6 different motifs that I present in there, and they are labeled as 1, 2, 3, 4, 5, and 6. And motif 1 and 2 represents that a generalistic, a specialist insect or fungus share the resource with another specialist insect or fungus. Motive 4, 5, and 6 implies that a bit more generalistic insects shares their resource, its resources, with more specialistic insects. And the motive 3 means that they do not share at all with animals or fungus that are more specialist than them. So what we observe is that even the data is more or less on 1 sigma deviation, there are not really large deviations. When motive 3 is overrepresented, the other 2 seems to be underrepresented. This is if I want the resource for myself, I want it for myself, and I do not share with no one that has a similar rank of specialization than I do. And the tendency to share that we were talking before, it's observed in the saprophytic interaction and in the symbiotic interactions, in which motive 1, 2, and 4, 5, 6 are overrepresented, while motive 3 is underrepresented. It is not observed, though, with the pollination interaction. And this makes sense because an specialist insect just have, in this case, 2 or 3 resources to collect. So that insect do not have many resources and do not want to share them. But we obtained that indeed they were sharing. So now we know that this sharing occurs in the more generalized insect with more generalized insects, or in the more generalized insects with more specialists. And this makes sense because the generalist insect have many more resources and at some point do not mind sharing some of their resources with more specialist ones. But the specialists do not have many resources, so they do not want to share them. And finally, we want to observe the how strong the environment is against some specific extinctions. And to do that, we perform a percolation attack. Usually a percolation attack is defined by removing nodes or hypereds. I have done both. And the small components are removed. But in this case, I'm not going to consider that the small components are removed, but just the completely disconnected nodes, because a small component can still work in the environment. This is an assumption. So what we observe is that with the null removal, the slope seems to be less sharp. And we observe that for the focused attack and the random attack, the focused attack is following the importance of the node with the degree centrality that we were talking before. Both of them present a threshold, meaning that they start increasing from the very beginning. So from this first point, we already have both extension in both axes increasing. But in the focused attack, we destroy one layer completely at the 25% of removals, while in the random attack, it happens in the 82%. This is important because if we remove one of the key layers in the ecosystem, we can consider that the ecosystem is completely destroyed. It will not be able to still work. The case of the Iph removal is a bit different. The thresholds are different. In fact, we start increasing and in a quite sharp way with the focused attack, in which now we follow the Iph order. So things that we are working on the plant projection just by extincting some animals, so by removing a few Iphs, we have a huge extinction on the plants. This happens mainly because of the plot I was presenting before in the dispersal network, in which I was saying that the plants were not that important, but we do not know if these plants can generate cascade effects, which in fact it's quite likely. And now we have that the threshold is in the very first beginning for the focused attack. Well, it's in the 50% of removals more or less in the case of random removal. So the thresholds are really different. And the increase is really abrupt. So just to sum up a little bit everything, we have observed a tendency to share that was quite shocking because we observed that tendency to share even in species that are supposed to have a competitive interaction among them. We observed that with the overlap and we confirmed that with the motives for the case of saprophytic and symbiotic networks. Then we observed the importance of the nodes and we used this importance to perform a percolation attack on the network. And we observed that especially in the case of Iph removal, there are sharp transitions. And this is quite important because it shows which species we need to protect the most in the ecosystem from the human actions or from the environmental changes. Because as you saw before, with just a few extinction on animal species, we lose a lot of plants. So we need to protect them from the changes in order to keep the ecosystem. Well, we are in the very beginning of a new kind of analysis in the case of ecology. Hypergraphs had not been used before or not much used. And of course, there are much more to do. So in here, I suggest 3 different points that I think they are essential to consider with this research. And first is the analysis of each layer, because the distribution of each layer, because, well, as you know, experimental data usually is incomplete because of the difficulties of collecting the proper data. So if we have the hyperage distribution, we can complete it via some base loop algorithms, which in fact, what they do is to add the hyperage most likely to be there in that network. Then we could assume correlations between the layers. And what do I mean by assuming correlations? The Iph removal in the percolation process was performed on the aggregated graph. So I was not considering if there was in one interaction or in the other one. But it is interesting that if we have an extinction in the dispersal network, for instance, that plant is not getting the dispersal interaction, so it cannot reproduce, or it will reproduce in much less amount. So we can consider that even though the node is alive in some other layers, the plant indeed is not, because it will get extincted just because it has no dispersal interaction. Just the opposite, for instance, if the node disappears from the herbivorous interaction, it means that the plant loses one of their main predators, so they can reproduce more freely without having predators that control the population of that plant. And finally, what I personally consider more interesting, it will be to perform a dynamical analysis in which we perform this percolation process we have done, but we add rewiring. And what do I mean with rewiring? Well, rewiring is that if we have an insect, for instance, which collects many different plants, and one of those plants get extinct, the animal will try to find an equivalent resource, and that can happen with a certain probability. And even if the animal do not find that resource, it can be that it adapts to the new environment and it is now able to collect new resources. And that also can happen with a certain probability. So that was all. Thank you for your attention. And if you have any question, please go ahead.
Thank you, Daniel. Okay, so now we'll proceed with the questions. First, Miguel. Okay.
Yeah, thank you, Daniel, for the presentation. So first question for me would be a bit, if you can elaborate a bit more about the motivation of the work. Because when I read your thesis and also a bit in the presentation today, I had the impression that you assume that using a more complicated tool, so the hypergraph analysis, you will immediately get better results in the analysis. But you don't go step by step to explain why this is the case. Can you say in a few words why you assume that a more complicated tool would give you better results in this case?
Yeah, well, when we reproduce any kind of system, we want to model it. Of course, we want to make some assumptions because we cannot take into account all the characteristics of the systems. So the complex networks that have been really used in ecology have the limitation of the pairwise interaction, which in fact is a big limitation. And I think it mainly shows in the point I was talking about of the abrupt transitions, that they haven't appeared in this work, but because we are in the very beginning of the analysis. But those transitions are really important in ecological systems because, well, an abrupt transition, first of all, means that, for instance, consider a species, the population is decreasing, but you are like, okay, there are still a lot of population, we do not have problems, the species is not going to get extinct. And all of a sudden, it drops. And see, we have this species extinct. So this is the reason we want to have this kind of sharp transitions in our model. Because even more important, when we have this kind of transitions, usually it shows stress cycles. which means that it is not that easy to reintroduce back that species into the ecosystem. So with the models in complex network that we had so far, we didn't have these transitions, and we didn't know exactly the points in which it was dangerous, let's say, in which the species was going to really extinct because the transition was not clear. With hypergraphs, we expect, even though it haven't happened yet, we expect to have these behaviors. So it is to model with more fidelity the systems, and in a specific point that we consider is important for the ecosystem.
Right. And now I have a second question now regarding your contributions, your personal contributions to the work. You mentioned that you have developed some Python codes for the analysis. So this is original, I assume. And I was wondering also for the data, did you have to clean the data that you got, or it was quite easy to use right away, or how was that?
Well, I had to move some things just to be able to export it to Python, but in general, the data was really clear. So it was just a .txt with 3 different columns, just that at some points, the style, let's say, was not the same in all the rows. So I just need to fix that, but the rest was completely organizing the data. I didn't need to do much about that.
Good. And now when seeing the results, I had the impression that the percolation analysis was useful and important. Did you have the chance to discuss this back with ecologists?
Sorry?
Did you have the chance to discuss with the people that gave you the data about the results? Did they find anything interesting about it?
No, I didn't, because this was this result was at the very end of the project. And at that point, well, the ecologists that we were doing the project, this is on holidays. So it is not like disturbing her right now, but I guess that at some point she will see it. And
okay, and what about other parts of the results? Did you have the chance to discuss with them?
Some of them, at some points, I would have liked to have more, not maybe ecological discussion, but maybe some literature to defend some of the results. But yeah, at some points we had ecological assessment in some of the measurements, especially in the part of the motifs and the meaning of the generalist and specialist and how they interact. That in that part we have ecological assessment.
And then maybe a final question now. What is for you the biggest potential of this approach?
Well, I think that in the percolation process, even though we do not see it yet, we start to have these sharp transitions. So I think that the best potential is not that much the structural characteristics, which of course are important because we first need to understand the structural characteristic of the network, but the dynamical analysis we can run with this kind of networks, that even though they are still models, and of course they do not have into account all the characteristics of the ecosystem, I think they can reproduce with really good fidelity the real behaviors in real ecosystems.
Thanks.
Thank you.
Thank you. I have a few questions, and one is somehow related to the first question that Miguel asked you. I mean, the network that you have starts from a bipartite network. You have plants and animals and fungus, so animals and fungus on one side and plants in the other. So in principle, you could do all the analysis on this bipartite network.
Without performing the projection, you mean?
I mean, yeah, with the original network. Now, the question is, what advantages do you get by performing this projection in the hypergraphs? Something that you could easily see in this system, something that you can clearly identify that is not easy to identify in the other thing. I understand, of course, that everything that you get in one system, you get in the other one, because of course the hypergraph comes from the bipartite network. But the point is anything that is really identifiable here or more clear by doing that, something that you would emphasize?
I would say that when performing the projection, the meaning of the Iph in whichever projection we are working is clear. So for instance, let's think on the plant projection again. The nodes are the same, are the plants. Each node is a plant, that's clear, no problem with that. But before in the bipartite graphs, we have an insect and we have many interactions, many different interactions. And we are considering them at some point in an individual way. So I think that after performing the projection and considering those interactions as a, let's say, unique interaction, the meaning of the insect working as an interaction with all those plants is clear, because you see a bunch of plants presented and an insect that collects all that plants. So not that collect one plant, then other, then other.
So it's a so say that it's an easy graphical interpretation of the outcome network.
For me, theoretical, yeah, well, graphically it's easier to have the interpretation. Also, I guess that at some point, if you keep with the investigation, it will have real effects that you just can obtain in hypergraphs, I guess. But also computationally, I think it's easier when it comes, for instance, to the percolation attack. I think it's easier to see, okay, I have this node, I have this hyperage, I just remove it. Okay. While in the other way, we need to take into account all the pairwise interactions and remove all of them. I also think that computationally, even there is not much done in hypergraphs. For some of the analysis, it can be much easier to perform by using hypergraphs than by using the original bipartite networks, in which making one change implies change a lot of interactions. While in the case of the hypergraph, making one change means removing that hyperage, and that's all. So
which is sort of equivalent, no? Because changing that hypergraph is the node that you have eliminated in one of the bipartite.
I mean, of course, it's equivalent in the meaning that you can create a list with all the interactions.
So let me put the question in another form. When you construct the network, you do the projection and do something else. You simplify your network. So you remove duplicated wings, and you remove self wings that point out to oneself. Okay. In one sense, this can make the network more fragile or more robust to changes.
Yeah, probably yes, because you do not have those duplicates, which gives strength in the case of changes.
So then, in what sense, for instance, one can say the analysis performed on the hypergraph or performed on the bipartite network provides the same result, similar results, is more easy to do, the results are more realistic for whatever reason.
Like, of course, when assuming this simple hypergraph and we are removing duplicates, it's going to have to be a simple model. But as I was saying, I think that mainly is computational, because even though you can do all of that in the bipartite network, you need to create a set of lists or similar. Maybe someone can think on another way, or working directly on the adjacency matrix. But if you do that in the bipartite graph, it's like really working with the hyperage, because guess a node and imagine a node that will act as the hyperage, and you create a list of all the plants that it connects to. Well, yes, you can do that on the bipartite graph, but in fact, that's the same than doing the projection, because you have the hyperage. So I think that all the ways I can think of to analyze the bipartite graphs come to build the same material that I have needed to build to perform the analysis. So in fact, it's like doing the projection.
Okay, understand. Okay, another question. You didn't mention here in the presentation, but in the report there is. You mentioned that you use some discrete exponentials.
Yes.
What do you mean by a discrete exponential? You mean a geometrical distribution?
I mean that when computing the normalization constant for the distribution, I did it as a sum instead of.
So let me put the question in another way. The exponential is a distribution that can take any value. Yeah. 3.7, 2.92, 74. Yeah. The geometric distribution, which at some point the exponential distribution can be as seen as the continuous limit of the geometric distribution. The geometric distribution takes only integer values. The distribution you are using here takes integer values only, or can take any value?
All integer values, because
So then it's not an exponential, it'd be a geometric distribution.
well, that's why I call it a discrete exponential.
Okay,
But
so,
in fact, it's
so by
not an
discrete exponential, you mean if it is a
that
geometric
it just can take integer values.
Okay, so it's not so by mean that you mean the geometrical distribution.
But is it the same than the geometrical distribution?
mean-
Right now I cannot think on the form of the geometrical distribution, but it's still the form of the exponential.
It has a similar shape than the exponential, but it only takes integer values.
But similar or the same.
Did you attend my lectures at the master?
I did, but there were many
So
functions.
then, yeah.
Well, like, I do not see if it's exactly equivalent, but the point is that if I present in here the exponential, well, this goes like this, more or less, you can imagine. Before, as you said, you can have all the continuous values. You can have here, for example. Now you just have the discrete values. So the distribution is the same.
Yeah.
But when you perform, like you have, and distribution is this way.
Yes. Yes.
But when you perform when you calculate the normalization constant, before you were calculating it as the integral of this.
But if it takes discrete values, it's probably a geometrical distribution, and the way to normalize the geometric distribution is properly defined.
So maybe then I could have used the geometric distribution, but also the point is that I do not know how it will have been the fit with the maximum likelihood estimation.
That's another question. Is that was going to ask? Did you use the exponential because it's a technique to fit the equation and it's not for the geometric? Because you explore if there is fitting methods for the geometrical distribution.
I didn't compare. Like, first idea was to compare to an exponential, and after to perform the fit to an exponential, and after performing the fit, we thought that it would have more fidelity if it was discrete, because some of the values are restrained. An insect cannot collect 3.5 plants, for instance. And then after doing that, we think on a way of discretizing, let's say, the exponential. Maybe if we will have think on a way of having a discrete fit from the very beginning, we would have thought then in the geometric distribution.
And also, is there any, say, theoretical reason, arguments given in lectures or whatever, to think that this distribution has to be exponential, or is just that you find that that is that? I mean, is people say no, the distribution of whatever, the Iph rings is found to be exponential somewhere? No.
At some point, I have discussed with Victor and Lucas, but it's something I don't fully understand, and that is why it's not included in the thesis. But having this exponential distribution means that adding a node to the average do not cost extra energy.
No, I'm saying what it means. I mean, is that somebody says, has reported the lecture. No, we expect to find exponential distribution for this sort of systems or biological systems or graph.
Well, we do not present a cutoff, for instance.
Yeah.
I will think that in a really large ecosystem, there is no natural cutoff. So for instance, that's something that the exponential have. Also, it can have the power law, which we also try to fit it. But the power law does not have this condition of the energy that, as I said, I still don't fully understand. But if you want to add an average, a node to the average, it will cost extra energy. So, as I said, I do not understand completely the equivalence.
So do you think that this is an important argument for ecosystems, the fact that you could add?
I will think that adding just on the meaning, on the theoretical meaning, that adding a new node is something that do not cost extra energy to the animal. Because it's just like, okay, now I can collect this resource. Why this could cost an energy?
Understand. Now, you mentioned the different networks separated, and some of them has very low statistics. And then you mentioned at the very end the possibility of using somehow methodology to fit whatever are the missing links on those. So do this assumes that you are going to measure the network on a different ecosystem, whatever, and infer what is the distribution of wings and then be reproducible in another ecosystem? Because of course, for the ecosystem that you don't have the data, so you don't know what is the real distribution of that. I mean, because you don't have the data. So if you have to infer that data to fill the missing wings, means that you either have to take from another ecosystem or from another interaction in the same ecosystem. So the question is, to which extent do you expect, say, for instance, pollination or whatever interaction to be equivalent in different ecosystems to be able to extrapolate the data from one to the other?
Well, I do not have much information about that, but I do think that some of the behaviors will be, in fact, general behaviors. So the behavior for the aggregated graph, in fact, I think that is something that can be the exponential behavior that can be in any ecosystem, because there is no reason to think that it is something limited to this ecosystem in particular. But of course, saying that without analyzing other kind of data, it's something.
Okay, that's the basis of the hypothesis that you assume that you could infer links that are missing.
Yeah, but inferring the links that are missing, then
means that
I will do it in these specific ecosystems. I cannot say.
No, but you do it assuming that you know the probability distribution, which you don't know.
Of course.
So you have to infer that probability distribution from something else.
Or maybe there are some mathematical ways in which you can obtain a, let's say, not really bad fit with the few data that we have. Or maybe at some point we also wanted, or we thought on the question that, okay, if we have a sum of exponential distributions, do we obtain an exponential distribution?
Yes. If you have a sum of two exponentials, it's an exponential. The exponential is a stable distribution.
Which
no.
do not imply that each individual distribution is going to be exponential, but it is something that points towards it. So the question will be, is there a way of summing random distributions and obtaining an exponential distribution? It's just a particular case that happened in this analysis. Like, can we infer the shape of each individual layer by knowing how the total, the aggregated graph is? So the point is that the methods I think of were not that much on adding data from another ecosystems, but doing it in a mathematical way that I didn't investigate much, and it's something really difficult to do.
Okay, thank you.
Okay, thank you. Well, I read the master thesis. I find it interesting. So there are some typos and mistakes that maybe you rush a little bit at the end, but I can give you so you can correct that. Okay, and I have some comments. I have to add up to the point that both Miguel and Pedro raised, that about the justification of using the hypergraphs instead of just the normal link, the normal network. Okay, and in particular, one thing I read and I immediately marked in red in the memory, and then you say it again here in the presentation, is about one of the justifications you give is that the hypergraph allows to describe the discontinuous transitions, and I don't understand this. I mean, the discontinuous transition probably has to do more with the temporal dynamics, the local dynamics, or the non-linearities in the interactions or whatever, but not on the network of interactions or something like that.
Yeah, but when you have the representation, you can run dynamical analysis on that representation, and on those dynamical analysis, then you obtain some transitions that they can occur. As you say, usually this.
I don't understand what you say. These transitions will occur in the hypergraph and not in the normal representation.
It is something that is documented in the reference I give in there. It says that even though the complex networks can show this kind of behavior, they have been shown much more common in hypergraphs. It's something I didn't investigate in more detail, okay, but yeah, it's documented in there, like they are more common to be present.
Okay, it's not really clear to me at this point, but yeah, can discuss in more detail later. Okay, so well, basically all the other things. I also was concerned about the fact that you lose when you do the how you call it, the
perform the projection, you
the
mean?
projection that they use the links that go to the same node, or you put two links, you simply just put. I was concerned whether that was a too strong simplification of the interactions or not, but
maybe it is. In fact, we thought about it since it's like the very beginning and there is no much mathematics about it, including the self loops makes everything much more complicated, mathematically talking. So we made that assumption, we made that simplification, but in fact, even though I haven't written it in the further steps, I think that it will be something interesting to add. So in further research, it will be interesting to consider the Iph, because as you say, we are removing a lot of species that are not being considered just because they just link to one plant. So in this case, it is a simplification. I think it's quite a strong simplification. I think that is something, if you want to obtain a better model, that should be fixed.
Okay. Okay. So then, assuming everything is correct, then you do the analysis of all the statistics of the rings and degree, whatever. And I find interesting the attacks, no? So these the percolation attacks. So, but you present the result, but you say nothing about. So, I mean, what are for instance, what is that plant that is the most one that has more links that you remove? So, what plant is that? Who is that? Have you just say the?
I think that
you just told write the scientific name, and do you know anything else about that? So
I haven't investigated much, but this is the plant. This one over here.
Okay,
but I didn't investigate much about the specific plants and species because, well, the plants we just have 47, so it's something that we could do. I tried to explain some of the results, but how they were classified, so the family and the order of the plant.
Well, no, but I mean, where do you find the plant? Is everywhere? Who is that? Why is so?
Why is it that common? Why is it that well connected?
Why is that important?
I guess that because of the resource it gives, but that is the reason I try to look some of a correlation or some of indicators by looking at the families and the orders, because I was, okay, let's see if all the most connected plants are the same order, or let's see if they are the same families, or let's look about this kind of family of plants to see if they have some specific condition. But there were not seen to be a unique behavior, and it was something really related to ecology. And at some point, many things I didn't understand because, well, I don't have background enough in ecology. So I think most of the classifications and the results can be, in fact, as you said, grouped by the order of the family and or the kind of the species and the resources it gives. But this is something that to do it, at least I really need some ecological assessment behind it because it's really particular.
Yeah.
But yeah, I think, like, if it is what you mean, I think that some of the tendency observed could be explained by considering the families and the order and similar real characteristics of the plant and group them some way.
Okay, so just one final question in just reading the conclusions. So from your analysis, you arrive to some conclusions, and there is one that like you to comment is that the plants do not tend to use animals for both dispersal and pollination.
Yeah.
Why is that? Why is that you arrive to these conclusions?
Well, I thought, because I wrote that because of the dispersal and pollination network. As you saw, there were not many nodes in common, and most of them had just one node, like one node repetition. And I thought about the reason this can be. At first, I couldn't come up with any explanation. What I thought later on, and I haven't found it in the literature, and I think it should be documented some way, and it will be interesting to know, it's that if you have, usually dispersal is performed by bigger animals, yeah, so let's say a bird, for instance, any bird, and pollination is performed by insects or really small animals. So if you have a huge bird and a small insect going to the same plant, it is likely that the animal will also eat insects and it eats the insect. So like in some way, the plant has evolved in such a way that it do not want to have both interactions because then one of them consume the other one and you do not have presence in.
But you have the predation data also, but you don't have that detail, I guess.
You mean if I have in the data the name of the...
You had the pollinators and the...
I have the names. I have the names, so I could look if in fact they consume insects or not. Or yeah, I could check at that. Sure, it will have been interesting to.
Okay, that's all. So thank you very much. So now the panel will deliberate and give you much. So
Sure.
you please, can you leave the room?